In this video, we're going to switch back to rectangular coordinates from polar coordinates, and we're going to consider a new type of curve called an ellipse. So I've drawn a rough sketch of an ellipse here, centered at the origin, and you know what an ellipse looks like, of course. It's just an elongated circle. So our study of ellipse is going to be closely related to our study of circles back from chapter 1. Now, it's very easy to think of a geometric definition of a circle. A circle is just the set of points in the plane that are a fixed distance away from a given point. And that given point, of course, is the center of the circle. And the fixed distance is the radius. An ellipse, on the other hand, also has a geometric definition, but the geometric definition is a little bit more complex than the geometric definition for a circle. So an ellipse is a set of all points in the plane, the sum of whose distances from two fixed points. So for an ellipse, we deal with two fixed points rather than a single fixed point. The sum of these distances is a constant. These two fixed points now on the plane are called the foci of the ellipse, so that's plural. Each one of the fixed points is referred to as a focus of the ellipse. So in this definition, I've labeled these two foci f sub 1 and f sub 2. So in this picture that I've drawn of this ellipse, I've put the two foci along the x-axis, and I've drawn the ellipse so that both of these foci are equidistant from the origin. In other words, the center of the ellipse is the origin. So this definition now is a little bit complicated to understand, so I've got it illustrated for you. But again, consider the set of points and consider these two foci such that the sum of the distance from this set of points to the two foci is a constant. So let's let xy be a variable point on our ellipse, and then let's draw these two distances from xy back to these two focal points. So here's the distance sort of represented by this line segment from this variable point xy on the ellipse back to the focus f sub 1. And then, of course, here's the distance from this variable point xy to this second focus f sub 2. And again, what's supposed to happen is if you add up these two distances, that has to be a constant. That has to be the same amount for each point on the ellipse. So if I were to pick another point on the ellipse and calculate its distance to f sub 1 and f sub 2, so calculate these two distances. Let me sort of draw a picture of that, of those two distances. So if I were to calculate these two distances and add them together, these two distances, that would be the same sum as the distances from this point xy to the two focal points summed up. So that's the geometric definition of an ellipse that we're going to use. I'm going to call this this fixed sum of these distances, let's call that d. So remember, that's a sum of distances to these two focal points. All right, so what I want to do now is using that geometric definition, and it's not completely, of course, easy to understand why when you apply that definition you get an ellipse, but you do, okay? Not nearly as easy to understand as the geometric definition for a circle. But we want to take this geometric definition now, and what we want to do is derive an equation for this for the points on the ellipse. So in other words, an equation whose graph would give us this particular ellipse. All right, so I'm going to assume now, as already mentioned, that these two focal points are equidistant from the origin. So I've got them located on the x-axis. That's just for convenience here. The two focal points could really be located anywhere on the rectangular coordinate system, but I've drawn them on the x-axis. And again, I want to assume that they're both the same distance away from the origin. So one of them's to the right of the origin and one of them's to the left of the origin. And so we'll assume that this first focus, f sub 1, is located at the point minus c, comma 0 on the x-axis. And then the second focal point, f sub 2, is located the same distance away from 0, but on the positive side of the x-axis. So it would be located at the point c, comma 0. All right, so what we're going to do now is, starting from our variable point x sub y, which is on the ellipse, right? Let's calculate these two distances from x, y back to the two focal points. We're going to add those two distances up, and then, of course, that has to give us this constant amount d. So that's true for any point on the ellipse. Again, calculate those distances back to the foci, add that up, and you always get this same value, okay, which just for in this definition, I'm going to call that value d for distance. So let me scroll down a little bit here so I can give myself some room to work, because there's a little bit of a calculation that we have to do here. So first, let's calculate the distance from xy back to f1. So we're just going to use the distance formula, right? Okay. And so let's see, that distance would be the square root of, well, you take the difference in the x coordinates, right? Square that. So that would be x minus this x coordinate of the focus, which is minus c. So x minus a minus c would be x plus c. Square that, right? Okay. Plus then the distance from y, from this point, I'm sorry, the difference in the y coordinates between these 2 points, x comma y, and minus c 0. So of course that's going to be just y minus 0 squared, which of course will just be y squared. And then you take the square root of that sum. So that's the distance from f sub 1 back to our variable point x comma y, which again, x comma y really represents any point on the ellipse. All right, now let's add in the distance from x comma y to f2. So here we would get the square root of, again, I'm going to take the difference in the x coordinates. So that's going to be x minus positive c here, squared, right? And then again, we end up here with y minus 0 squared, the difference in the y coordinates between these 2 points, and then you take the square root of that sum. So there's the sum of the distances from xy back to the 2 focal points, and remember that sum has to be always this fixed value d. Okay, so starting from this equation now, we're going to simplify this equation, and we'll end up with a simplified version of the equation whose graph corresponds to this elliptical curve that we see here on the rectangular coordinate system. By the way, notice, of course, the ellipse is not a function, right? So the equation that we get will not be the equation for a function. All right, now I'm going to have to do a little bit of substitution here to make the remaining algebra in this simplification a little bit easier. So I'm going to write the d in kind of a strange way. I'm going to write this as 2 times d over 2. Of course, 2 times d over 2 is just d. So I'm just changing the right-hand side, the way the right-hand side of this equation looks. And the reason I'm going to do that is because I want to make a substitution. I want to let d over 2 be represented by the variable a. And this really turns out to be just a convenience in simplifying this equation a little bit later on. So if we let a equal d over 2, and then I substitute a for d over 2 in this equation, then the right-hand side of this equation becomes instead of d, it becomes 2 times a. Okay, so let's rewrite this somewhat, just to get rid of that, some of that substitution. So I have x plus c squared plus, of course, y minus 0 squared is just y squared, and then plus the square root of x minus c squared, and then again plus y squared, and then is equal to, instead of d, I'm going to write the right-hand side of the equation as 2 times a, but remember a is just the same as d over 2. Okay. Now, what I want to do to simplify this equation is I want to get rid of the square roots. So I want to ultimately end up with an equation that doesn't have any square root symbols in it. And so that means I'm going to have to square both sides of the equation. Well, to make that process more efficient, first I need to isolate one of the radicals on one side of the equation. So I'm going to subtract this radical, the x plus c squared plus y squared, the square root of all of that, from both sides of the equation before I square both sides of the equation. So I'm going to end up here with x minus c squared plus y squared is equal to 2a minus the square root of x plus c squared plus y squared. Now I'm going to square both sides of the equation. Okay, so now this is where I have to do a little bit of algebra. All right, so let's square both sides of the equation and let's see what we get. Well, of course, squaring the left-hand side of the equation is really easy. So I'm just going to get x minus c squared plus y squared. So the radical just is canceled there. And now I have to square this quantity on the right-hand side of the equation. Okay, so let's just be patient and see if we can do that. So let me write that out, actually. So I have 2a minus the square root of x plus c squared plus y squared, and then times itself, right? Because that's what it means to square this quantity. See if I can squeeze all that onto the paper here. So that just barely fit. So let's be patient in squaring out this quantity on the right-hand side of the equation. So I have x minus c squared plus y squared is equal to, well, 2a times 2a, I think that's 4a squared. And then, of course, you're going to have 2a times this radical twice, right? 2a times minus the square root, and then you'll have 2a times minus the square root again. So I think that's going to be altogether minus 4a times that radical. So that's x plus c squared plus y squared. And then, of course, you're going to have the radical multiplied by itself. So you have minus the radical times minus the radical, and that means just that the square root is going to get canceled, right? So we end up here with plus. It's minus times minus is plus, so this is very convenient. So we end up with just the quantity underneath the radical, right? X plus c squared plus y squared. All right, so that's not looking so much simpler, correct? But it is somewhat simpler because at least we're down to one square root. Now, at this point, I'm going to go ahead and expand this product x minus c squared and x plus c squared because I think we'll get some cancellations. and that may benefit us in the long run. So when you multiply x minus c times itself, you're going to get, if you do that correctly, you'll get x squared, and then I think minus 2cx for the middle term, and then plus c squared. So if you're curious about that, just do that on paper by yourself. Take x minus c and multiply it by x minus c. This is, I think, what you'll get, unless I'm just thinking completely incorrectly. And then is equal to 4a squared, and then minus 4a times, 4a times this radical that we still have, and that's, we've got to get rid of that also eventually here, but it's still here for the time being. And then at the end here, well, we're going to expand this product x plus c squared, right? So that will end up being x squared plus 2cx, and then plus c squared plus y squared. Now, at this point, we are going to get some cancellation because I've got some terms that are appearing on both sides of the equation, and that's exactly what I want. The x squareds will cancel, and the c squareds will cancel, and the y squareds will cancel, right? So you see things really are looking better. Unfortunately, we can't cancel the 2cx, right, because it's negative on one side and positive on one side, so that doesn't cancel. But several terms there disappeared from both sides of the equation. So let's see what I'm left with here. I've got minus 2cx on the left-hand side is equal to 4a squared minus 4a times the radical, of course, plus y squared, and then plus 2cx. All right, now, I've got to get rid of the second square root. So that means I'm going to have to square both sides of this equation again. You're starting to dread that already, right? But let's see. Before I square both sides of this equation, though, to eliminate this radical, I've got to isolate this radical on one side of the equation. So I'm going to do that by taking the radical and moving it to the left-hand side of the equation, and at the same time I'm going to take this term minus 2cx and I'm going to move it back to the right-hand side of the equation. So when you do that altogether, you end up with, and I've also got to take the 4a squared. Oh, no, I can leave that on the right-hand side of the equation. So I end up here with 4a times the radical, but never fear, that radical is getting ready to get squared shortly, so we'll be finished with the radicals. So I have 4a and then times the radical is equal to, and let's see now what's left on the right hand side of the equation. This looks like 4a squared plus 4cx. Okay, so we're making a little bit of progress here, and now I'm going to square both sides of the equation. Oh, let's see. Actually, now, I think I can do something first, though. Notice that everything here is a multiple of 4, so that's very convenient. That means I can divide both sides of the equation by 4, and I can get rid of all these coefficients. So let's do that. I almost forgot I could do that, and then I was going to end up with a messier equation than I wanted. So I end up with a, just a times this radical is equal to a squared plus cx. All right, now finally let's square both sides of the equation. So it won't be that bad to square the left-hand side of the equation. The right-hand side of the equation now is going to be a little bit uglier to square, but not bad. So I'll end up here with a squared times the quantity underneath the radical, which is x plus c squared plus y squared. So the radical is gone here. And now when you square out a squared plus cx, when you expand this product, you're going to get a to the 4th power plus, I think, that's going to be 2a squared cx, right? And then plus c squared x squared. So now we take a deep breath. So we have made some progress because now both of the radicals are gone. Now let's finally here, let's expand this product x plus c squared, which I guess we'll also have to multiply by a squared eventually. But let's expand that product first. So that's going to be x squared plus that 2cx again that we've seen several times already, plus c squared plus y squared. Right, that y squared is still here, but this is x squared plus 2cx plus c squared is the quantity x plus c squared, times the a squared is equal to, and then we still have our three terms on the right-hand side of the equation. Okay, now I'm going to multiply through, I think, by the a squared. So I have a squared x squared plus 2a squared cx plus a squared c squared plus a squared y squared. Everything is multiplied by a squared here, right? Is equal to a to the fourth power plus 2a squared cx plus c squared x squared. And now I get another cancellation. That's nice because 2a squared cx appears on both sides of the equation. So I can get rid of that, and that's going to make things look quite a bit nicer. Not perfect, but a lot better. So I have a squared x squared plus a squared c squared plus a squared y squared is equal to a to the fourth power plus c squared x squared. All right, things are shaping up nicely, I think. All right, now, here's what I'm going to do next. I'm going to gather terms. So I'm going to get my x squared and y squared terms on one side of the equation, and then I'm going to get my terms that don't involve either x or y on the other side of the equation. So let's see, I'm going to have a squared x squared. That's an x squared term, so I'll keep that on the left-hand side of the equation. Here's an x squared term on the right-hand side, so I'm going to move that to the left-hand side and change the sign. So I have a squared x squared minus c squared x squared. And then we'll keep the a squared y squared on the left-hand side of the equation. But this term doesn't involve either x or y, so I'm going to move that to the right-hand side of the equation. So I have a to the fourth minus a squared c squared. All right, so from this, I'm going to factor from these first two terms on the left-hand side. I'm going to factor out an x squared. So I'm going to write the factor x squared behind parentheses here instead of in front of. So I have a squared minus c squared times x squared plus a squared y squared is equal to, and then from the, notice that on the right-hand side of the equation, from both of these terms, I can factor out an a squared. So that's what I'm going to do, and that leaves me with a squared minus c squared. All right, now I know you're wondering at this point, what in the heck am I doing with all of this algebra? It looks very intimidating. But here's the sort of the last step. I'm going to notice that I have some very similar factors on the left-hand side and the right-hand side of this equation, namely a minus c squared and also a squared. So I'm going to divide both sides of the equation, or all terms in the equation, I should say, by a squared times a squared minus c squared. Now, why in the world would I want to do that? Well, you're going to see here some nice things will happen. So I'm dividing every term by a squared times a squared minus c squared. So I'm allowed to do that as long as that's not 0. And notice then the right-hand side of the equation becomes very simple. That's just 1. And the left-hand side simplifies also because a squared minus c squared divides out from this first term. So I end up with just x squared over a squared. And then a squared a squared divides out from the second term, so I end up with y squared over a squared minus c squared. And that's exactly what I want. There is the simplified version, or almost completely simplified version of my equation for my ellipse. Now I'm going to make one final substitution here to make the equation even look simpler. I'm going to let b squared equal a squared minus c squared. So I'm just going to set b squared to be a squared minus c squared. And then that makes the equation look like x squared over a squared plus y squared over b squared is equal to 1. So you end up with a fairly simple equation in rectangular coordinates for the ellipse. But now you've got to remember that a, remember, that was equal to d divided by 2. And you also got to remember that b squared, we set that to be a squared minus c squared. Now, I want to show you, though, that a and b have important, although we appear to have invented them rather arbitrarily to simplify this equation, to make substitutions to simplify this equation. Actually, a and b have important geometric meaning. Okay, actually, look, if you substitute 0 for x in this equation, in other words, to find the y-intercepts, if you substitute 0 for x, notice you'll get just y squared over b squared, because if you substitute 0 for x, x squared over a squared will be 0. So you get you'll get just y squared over b squared is equal to 1, and that means that y squared will be equal to b squared, or y is going to be equal to plus or minus b. So in other words, notice that these are the y-intercepts. Plus or minus b will be the y-intercepts of the curve. And then by exactly the same reasoning, if you substitute 0 for y to find the x-intercepts, it turns out that the x-intercepts will be plus or minus a. You'll get x squared over a squared is equal to 1, because if you substitute 0 for y, this term will disappear, and so that leads you to x is going to be plus or minus a. So the x-intercepts of your curve are just plus or minus a. So that's sort of the geometric meaning of these values a and b, although we found a and b by what appeared to be just substitutions for convenience to simplify this equation. So let's finally fill this in. So this is a, that's one of the x-intercepts, and this is minus a, that's the second x-intercept. This is b, and this is minus b, the two y-intercepts. And the equation for this curve that you see here is just simply x squared over a squared plus y squared over b squared is equal to 1. And one other thing I need to point out that's very important is notice that since b squared is equal to a squared minus c squared, so you're subtracting c squared from a squared to get b squared, that implies that a is going to be bigger than b. And of course that's sort of represented here in this picture. You can see that the x-intercepts are going to be larger in magnitude than the two y-intercepts are. So there it is, the formula, the equation for this elliptical curve. Even though we started by defining this elliptical curve by using this rather complicated geometric definition, we see that that geometric definition simplifies to this fairly simple equation.